Hello all, this is Aman Soni and I'm here to tell about my digital image processing project. So the topic is multi-resolution bilateral filtering for image denoising. So before we jump to see how the code works, I want to talk about how the whole algorithm goes. Like what is the flow of the process? So this is the proposed method. We take our noisy input image and we take its wavelet transform and get the first level of approximation and detail subbands. Then we take second level of wavelet transform and we get second level of approximation and detail coefficients. Now there is a common theme that runs along the whole method, and it's that we apply bilateral filtering to the approximation subbands and wavelet thresholding to the detail subbands. This is what we're doing here, that we are applying bilateral filtering to the approximation and wavelet thresholding to the detail. And then, of course, since we decomposed everything into its approximation and detail coefficients, so we are going to reconstruct it also. So we are reconstructing our first level of approximation here after a certain amount of filtering, and then applying wavelet thresholding to the detail coefficient of the first level. Now remember that because this is the approximation line, so approximation coefficient line. So approximation coefficient of the first level passed through some sort of filtering, and then we got the bilateral filter once again to work on that reconstructed approximation coefficient. After since bilateral filter is applied, we get filtered value of the approximation coefficient of the first level. And in the in the final steps, we reconstruct the noisy image after certain amount of filtering using these first level of approximation and detail coefficient. And then finally, we apply the bilateral filtering once again to remove whatever the residual low frequency noise is. And in this way, we get our output, which is a denoised image. So keeping this process in our mind, let's jump to see how the code works. So there we go. So we are taking a noise-free image. So this is the IMRead function which reads the noise-free image, and these are the plotting commands which plots the input image, which plot the input image. So basically, now we are adding Gaussian noise to our input image, which is having mean 0 and variance 1000, which means a lot of noise. And we are getting our noisy image, which is nothing but input image plus the Gaussian noise. And again, these are the plotting commands which plot which plot this noised input image. So then we take our wavelet transform of the noisy image and get first level of approximation and then detail coefficients. Then we take second level of wavelet transform of these approximation coefficient and get second level of approximation and detail coefficients. Then, as discussed, we are going to apply bilateral filtering to the approximation and thresholding to the detail. So here we are applying bilateral filter to the second level of approximation. Now this 31 is this is the standard deviation of the range kernel. The spatial kernel in the bilateral filter. Uh, I'm sorry. This is the range standard deviation. Now, experimental results have shown that the optimal value for this range standard deviation is equal to the noise standard deviation, right? So, noise standard deviation was square root of 1000, which was around 31. So, yeah, uh, yeah. So, and then we take sigma d, which is the standard deviation of the spatial kernel, to be 1.5. Again, this is all empirical. These values are empirical. We did a lot of experiments and read some papers, and we figured out that these are the optimal values for sigma r and sigma d respectively. Fantastic. Now we are going we have to actually calculate the threshold value to apply wavelet thresholding in the next stage. So this function DDNCMP actually calculates thresholding value. S or H means soft thresholding or hard thresholding, and keep app. This is for approximate coefficient I want to keep. So we take threshold value from this function and apply this threshold value in our wavelet thresholding block. So this is the so here we are applying wavelet thresholding to the second level of detail coefficient. So see this CH second, CV second, CD second, which is second level of horizontal, vertical, and detail coefficient, and we get the thresholded outputs here. Now we are at the second level, and now we are reconstructing the stuff. So IDW2 is the inverse discrete wavelet transform, which is reconstructing the whole stuff. So filtered approximation coefficient of the second level, and these are the thresholded detail coefficient of the second level. This gives me the reconstructed approximate value, the reconstructed approximate coefficients. Then again we have to apply bilateral filtering on this approximation coefficient that we just reconstructed. So we are just using IM bilat filt to do the bilateral filtering. Now, the last thing that remained was to apply wavelet thresholding to the level 1. So these were the level 1 detail coefficients, CH0, CV0, CD0, and then again W thresh. W thresh is the function that applies wavelet thresholding, and threshold value we have just taken from that DDN CMP function here, and then we are inputting that threshold value here. In the final stage, we have to reconstruct our image. So this is the approximation coefficient of the first level, which was filtered. And these are the approximate detailed coefficient of the first level. So finally, we are reconstructing our noisy input image after a lot of filtering. So this is our final reconstructed image. And the last stage was to apply the bilateral filtering to this finally reconstructed image. This is what we are doing here, applying the bilateral filtering to the final reconstructed image. And the data, the sigma R and sigma D value, we have kept the same throughout. And here we get our denoised image. Once again, these are the plotting commands which plot the denoised image. Now, here we are calculating the SNR values. So this function, these three lines calculate the SNR value of the denoised image, whatever I've got after the filtering. So here is how it works. That this is the numerator, which is the input image power, and this is the denominator, which is the noise image power. So numerator upon denominator, this fraction goes inside the log base 10, and this gives me the SNR value in dB of the denoised image. Similarly, I am calculating the SNR value of my noisy image, which is the input power minus the noise power of the noisy image. So finally, when we run this code, what we get is, so let's just run this code and see the output. So yeah, because a lot of bilateral filtering is happening, that's why this code takes some time to run. And yeah, so we can see the output here. You can see the perceptual improvement and SNR improvement also. So this was our input image, which was free from noise. We added some noise to it, and you can see the drastic reduction in the SNR value, which is 15.20 dB. And here is the denoised image. We can see that the perceptual quality is much better. We can see that the perceptual quality is much better of the denoising. So this is about it. This is about the our DIP project. I hope we've been able to add some value. Thank you very much.